So in my previous video, I built this alternator powered bicycle. To summarize, I converted an old pickup truck alternator into a motor. I then successfully installed Hall effect sensors into the motor, and in the end, I was very impressed with the results. The only thing that I dislike about this setup now is the fact that I'm using two separate batteries. I have my 48 volt 18 amp hour battery, which is connected to the controller, and I have this 12 volt LiPo battery, which powers the field. I know I could probably eliminate using the 12 volt battery by using a buck converter, but I think an even better idea would be to convert this alternator into a brushless motor. While I was initially doing some research on permanent magnet alternators, I came across this article on converting an automotive alternator for wind turbine battery charging. In this article, the author showed step by step how he removed the field winding electromagnet from the rotor of his alternator and replaced it with a permanent magnet. I was really impressed with the way he did this and decided I would modify my rotor the same way. The rotor is made up of two pieces, each having 6 claw-shaped poles, and there's a strong electromagnet formed on a core inside. One set of claws is a north pole when the electromagnet is energized, and the other set is a south pole. The alternator that I'm using is meant to be pulled apart from the rear, and in order for me to do this, I first had to remove the rear bearing and also remove the slip rings, which I will no longer be needing. I used the 3-claw puller and a breaker bar to pull apart the two pieces. There it goes. The magnet that I'm going to be using is 3 inches in diameter, 1 inch thick, and has a 3/4 inch bore. Because the magnet is 1 inch in thickness, I will need to remove exactly a 1/2 inch of material from the inside face of each pole piece. This will allow the magnet to fit perfectly inside. This part is easy if you have a lathe, but I unfortunately do not, so I had to get this done outside of my shop. I definitely hope to buy a lathe one of these days. Once the parts were finished, I decided to clean off all the rust and give each piece a fresh coat of paint before installing the magnet. So I need to warn you guys that working with these magnets can be extremely dangerous and you need to be very mindful of your fingers. This specific magnet has a pulling force of 282 pounds, so you don't want to find yourself in a situation like this where you accidentally crush your fingers. Only work on a wooden or other non-magnetic surface, and generally try to keep all other metals away from these magnets as much as possible. Please be safe if you try to do this yourself. I don't want to be responsible for any broken fingers. Oh. The motor shaft is 5/8 of an inch in diameter and the magnet has a 3/4 inch bore. So in order to keep the magnet centered on the shaft, I 3D printed this sleeve. I'll be using my shop press to drop the magnet down into place. The method that I'm using is somewhat similar to what is demonstrated in the article. I'm using hose clamps and some flat rope to hang the magnet down from the piston of my shop press, and I line the inside of the press with wood so that the magnet wouldn't be directly exposed to the frame. This worked extremely well, and I then used my puller in reverse to drop the top pole piece down into place. I know this looks sketchy, but my fingers were out of harm's way. And there we go, that's the finished rotor. I did manage to ruin my nice paint job, but that's not a huge deal. Okay, so the last step is to put the motor back together and see if it works. So before I modified the rotor, I decided to record a couple of tests so that I could compare the performance of the electromagnet rotor to that of the permanent magnet rotor. I recorded an uphill test and an acceleration test. The tests were both performed at the same starting point with a fully charged battery. On the uphill test, you can see that the performance was almost identical. The only difference was the permanent magnet rotor had slightly better acceleration and was able to get up to 40 kilometers per hour on the uphill, while the electromagnet rotor got up to 38. But honestly, the difference isn't noticeable. For the acceleration test, I wanted to compare the time that it took to get up to 60 kilometers per hour. Once again, the results were pretty close, although the permanent magnet alternator got up to 60 kilometers per hour about 1 second faster, which once again isn't a noticeable difference. I did also record the top speed, and I was able to get up to 70 kilometers per hour. So once again, pretty much the same as what it was before. It's safe to say that there isn't any noticeable difference between the two rotors, although it's really nice no longer having to deal with the field battery and being able to completely eliminate the brush assembly. I've been really curious to find out how far I can actually go on a single charge and how much power the motor's using, so in order to do this, I purchased this cycle analyst. A cycle analyst is a digital dashboard and battery monitor with many features. It can precisely measure amp hours used, display watts, speed, mileage, and has lots of other settings. So I'm going to go ahead and install this thing, and then hopefully we can get an accurate reading of how far I can go on a single charge with this setup. Alright, I got the battery all charged up and the cycle analyst is good to go. So let's go see how far I can make it. Alright, here we go. We have gone a total of 2 kilometers. We've used 1.7 amp hours. Oh yeah, no problem on the uphill with old Rusty. No problem. Yeah, honestly, this thing has no problem on the uphills. We've gone 5.6 kilometers so far. And we've used 5 amp hours of battery. Alright, so I'm coming up to a really steep hill. Wow. That's right. Old Rusty just went up that hill. Alright, so we've gone 10 kilometers and we've used 8.73 amp hours. Of actual riding time, I have 16 minutes and 53 seconds. Yeah, 47.2 volts left. Let's see how far we can go. Okay, so we just lost power. Yeah, we're at 44 volts, so the BMS is starting to cut power. We've used a total of 14 amp hours and we've went 16.4 kilometers. Alright, I think that's it. Wow, that was a cold ride. Alright, so my total distance traveled was 16.6 kilometers and I used a total capacity of 14.3 amp hours. My average watt hours per kilometer was 38.6. And I do have regen enabled through my controller, but it looks like the cycle analyst didn't recognize that, so that's something I'll have to look into. My max amp draw was 99.5, which does make sense because I currently have it limited to 100 amps, but I think if I limited that some more, I would get a lot more range out of this thing. My max speed for that trip was 60 kilometers per hour, average speed 31.4, and my total riding time was 32 minutes. Total distance traveled 17 kilometers, and yeah, that's about it. I know that this motor isn't the most efficient thing in the world, but I really can't see myself driving it for more than 30 minutes at a time anyways, and I just think it's so cool that this bike is powered by an alternator and it can go 70 kilometers an hour. If you haven't seen the first 2 parts in this video series, I'll put a link to those in the description below. But as always, thanks for watching, and I'll see you next time.